Okay, so I do want to finish up our conversation on the three-phase circuits. So let me see, I'm swimming in notes here. So just to kind of summarize what we learned so far for three-phase circuits, we learned there's basically two ways of configuring them. You can either have the Y configuration or the delta configuration. And the key difference is that when you use the Y configuration, you have the presence of the neutral signal. So your voltages are measured relative to neutral. Whereas when you use the delta configuration, your voltages are not measured relative to neutral. They're measured relative to each other. So, and we were kind of, this is kind of where we left off on Wednesday. So where we left off on Wednesday was that we talked about having a Y configuration. So this is your neutral, and we call this VAN, VBN, and VCN. And what we talked about is that your standard notation is that VAN is equal to some magnitude times 0 degrees, and VBN, what's the relationship between VAN and VBN? Right. It's the same magnitude, same frequency, it just lags it by 120 degrees. Then VCN lags that one by 120 degrees. And if it lags that one by 120 degrees, that's the same as leading the original one by positive 120 degrees, which kind of makes sense. They're just evenly spaced, right? Each phase is 120 ahead of the one in front of it and 120 behind the one behind it. So, okay. So what we learned is that if you try to measure this voltage, okay, the voltage between two of the phases, okay, so whereas this is called your line whereas this is called your phase voltage, if you measure the voltage between two of the sources, you have what's called your line voltage. So in other words, we said that if you take VAN minus VBN, and we actually worked the math, you get, I believe we said it was VP root 3 angle 30 degrees. Okay, so there was this interesting conversion where if you measure the voltage between, like if you take the difference between two of these voltages, you get what's called the line voltage. Okay, so I'm trying to just at least introduce the vocabulary. If you're looking at it versus the neutral, you're talking about the phase voltage. If you're looking at it between two of the lines, you get what's called the line voltage. And there is a predictable, measurable relationship between the phase voltage and the line voltage. So the line voltage is always more than the phase voltage, right? It's a factor of root 3 more, and it leads. So it's more voltage, and it leads the phase voltage by 30 degrees. So you have that shift that's there. All right. So what would be What would be VBC? Any takers? It's all, I mean, so we figured out, we did VA minus VB. So we did this number minus this number. We worked the phasor. I believe that's how we did it on Wednesday, and to get the answer that you see on the board. So what if you did VBN minus VCN? Same magnitude, right? I mean, all the sizes are the same, right? Everything's got the same magnitudes. So you would also expect it to be VP root 3. What about the phase angle? You would expect it to, it's always a third of the way around the circle. So between any two of the phases, it always lags by 120 degrees. So, so if this is 30, if you lag it by if you go back 120 degrees behind it, you should get back to what, 90? Negative 90. Thank you. All right, and then if you do, so that was A to B, B to C, and then the third one, of course, is VP root 3 angle. You go another 120 degrees back. What does that get you to? 210, and so on. Okay, so we'll do a few examples now and kind of see how we can run some of these calculations. And the nice thing is that you only need to do the calculations once. Like, there are 3 phases, but it's the same calculation on each of the 3 phases. Yes, sir? Well, in theory, if you were to take this phasor minus this phasor and work the complex algebra, you'd get minus 90 degrees. Right? If you were to take one angle negative 20 minus one angle positive 120, and do that subtraction, which, I mean, this is VBN and VCN, so their difference becomes VBC. So if you were to take that difference, how would you take that difference? How do you always subtract complex numbers? Can't do it in polar. Got to do it rectangular. So convert them both to rectangular. What's that? Right. Convert them both to rectangular. Add the real parts. Add the imaginary parts. Then convert it back to polar, and that would give you root 3 angle minus 90. What's that? That's awesome. Then just do it in polar. Right. I mean, that's desirable. I wholeheartedly encourage you using your tools to make life easier for you. That's not bad. You know, there's a reason I drive to work and I don't take a horse and a buggy. Does this actually work out? Let me just try this real quick now that I'm curious. So this would be 120 negative cosine. So minus a half minus root 3 over 2j minus, I'm not going to do the calculation, never mind, that's a waste of time. Anyway, it should work out. You should get, I'll leave that as an exercise to the reader. That's the most obnoxious thing a professor can ever say, but there you go. All right. Okay, so let's work a couple examples and just kind of see this stuff in action. So the first example I want to do is example 11.2. It's on page 550 of your book and mine. Okay, so they're giving us they tell you there's a 3-phase Y-connected load that's being supplied by a 3-phase Y-connected source. And they're telling you the phase voltage is 120 volts RMS. They give you line impedances and load impedances, and they want you to find the value of the line current and the load voltages. What a mouthful. Okay. So this is like a little bit more of a straightforward one. We'll do a little bit more of a complicated one after that. So remember, whenever you're dealing with, especially with power systems, you actually have to consider the impedance of the line itself, right? You can't just talk about the impedance of the load. You also have to consider the impedance of the line that's delivering the load. So in this case, what they're telling you is you've got so you've got your sources. You've got a line impedance, and you've got a load impedance. And it's the same line and the same load in each case. Okay, and now they're telling you a couple interesting things. They're telling you that the phase voltage is 120 volts RMS. So what's my phase voltage? Where do I draw that? Right, they're telling me that phase voltage is 120 volts RMS. Where does that go? That nugget of information. Right, that's essentially telling me what VAN is. They're telling me that VAN is 120 angle 0. Okay, and likewise, I can calculate VBN and VCN if I want to. That would just be lagging by 120 and 240. But it turns out what's nice about this is that because I basically have 3 of the exact same circuit in a row, I only need to do this calculation once, because I know whatever I get for my current or whatever I get for my load voltage, the other ones are going to be the same, just lagging by 120 degrees. So I only have to do this calculation one time. So the other thing they're telling me is that the load impedance, the line impedance is 1 plus j. And the load impedance is 20 plus 10j. This is example 11.2. It is on page 550, or at least of the book I'm using. I can't speak for the pirated versions that everyone else is using. I would never encourage that. Okay, so we're asked to get the value of the line current and the load voltage. Okay, so we'll call that IA, IB, IC, and here's your load voltage, VA, VB, VC. Okay, so guess what? This problem ain't that bad. How do we solve this problem? Just Ohm's law, right? I mean, how do I get that? How do I get my line current, I sub A? Voltage over impedance, right? And always, it's the same calculation, right? It's amazing this even merits its own chapter. We're just doing Ohm's law all over again. So it's 120 angle 0 divided by, right, your total impedance, which is the line plus the load, which is what, 21 plus 11j? So now you got to do a division, in which case you've got a polar upstairs and a rectangular downstairs. It's not pretty. So you've got to convert the denominator into polar form and then do the division. All right, let's see here. So 21 squared, 11 squared, sum root. So your denominator is the same as 23.7 angle 27.6 degrees. All right. So you do your division. Oops, I did not need to do that. So 120, enter, 23.7, divide. So I'm getting 5.06 angle negative 27.6. All right? Easy. Okay, now, that was the current I sub A. Any takers on the current I sub B? Do we need to do this calculation over again? So let me just rewrite this over here. I sub A, we said 5.06 angle negative 27.6. Any takers on I sub B? Just subtract 120 from that one, from that phase angle. Same magnitude. Subtract 120 degrees. So minus 147.6 degrees. And ditto for C. We can either subtract another 120 from this one, or we can just add 120 to that one. It's exactly the same thing. It literally does not matter. I'll add. So I'm going to take 120 and add that on to 27.6. That gets me 140. That's not right. 120, enter. Thank you, 92.4. I didn't sleep enough last night to do numbers in my head. Sorry. I'll do party tricks another day. Yes, sir. Which one? This guy? Yeah, it was 21 plus 11J. I just converted it to polar. I added this. I added the line impedance and the load impedance. And I can add them because they're in series. Right? And we know how to work this stuff. Okay. Now I need to get the load voltage, right? The voltage across the load. So how can I do that calculation? Yeah. Just Ohm's law again, right? The current, I sub A, times the load, 20 plus 10J. Okay, so now you're back to calculator land. Get good at using your calculators, right? Figure out if your calculator can do complex numbers. It will save you time and errors. All right, so, well, they've done the calculation in the book. I will estimate that everybody can do it. They're getting 113 angle 1 degree. So they're getting V sub A equals 113 angle, is it positive or negative 1? Negative 1.1 degree. Okay? And then the same nonsense, right? You just subtract 120 degrees and 120 degrees again. So, minus 121.1, and VC equals 113 angle 120, 119, 118.9 degrees. So here's a question. If I came to you and I asked you on an exam situation, for example, to calculate the complex power in each of the 3 branches, what would you do other than panic? Because all that stuff we talked about, power factor, complex power, apparent power, real power, it's all here, right? I mean, just food for thought. It might turn up on an exam. Okay, like a whole chapter on this stuff that we haven't tested yet, so worth thinking about. Okay, but it'd be very easy to combine one of these problems with one of those problems, make a truly stinking exam problem. So let's think about that. In case you've forgotten, complex power is equal to voltage times the complex conjugate of current, and that winds up giving you, it has a real part and an imaginary part, and that was your regular old current that you've been calculating, your regular old real power you've been calculating all along, and then that's imaginary power. That's the kind of power that you get in inductors and capacitors. Remember we talked about inductors and capacitors had average power that was 0? It has average real power 0, but you can actually calculate imaginary power, and that's where your inductors and capacitors come to play. Anyway, I'm just saying, consider the possibility that those could be combined. All right, I'm going to do one more example and then call it a day. And I've lost that example. No, seriously, here it is. Okay. So I'm actually going to do example. Oh, I like this one. I'll just set it up. I don't think we actually have to crank the math the same way because it's the same. Once you set it up, it's reasonably similar. But I do want to at least get you started on example 11.3. 11.3 is a little bit sneaky because it looks a lot like the one we just did, but instead of presenting the source in a Y configuration, it gives your source in a delta configuration, which I will now embarrass myself by attempting to draw. And you're being told that and I think we're being asked to find the same things we did before, the line currents and the load voltage. All right. So at some point, it's just, I'm being asked to find the same things, but I'm being given different. My power is configured totally differently. So I know I want to find these currents, and I know I want to find my load voltages, but how can I proceed? Yeah?
Can you find the phase voltage by magnitude by √3?
It's that easy. Right. So the shortcut, the only cut, let's start with the long cut, right? The beating of a way to do this would be to apply Ohm's law, like basically do a mesh and node analysis on this. And you could do it, and you would get the right answer, all right? But it would just be unnecessarily complicated. But it would work, okay? It would totally work. So instead what we're going to do is we're going to redraw this. We're going to redraw this using an equivalent Y-connected load, Y-connected source rather. So let's see. So let me just write this over here. VAB equals 208 angle 0 degrees. So in essence, the way this relatively straightforward conversion works is I'm going to erase that source that was connected together, and I'm going to replace it with an equivalent Y-connected load. As long as I make the conversion, I'm good to go. So what is my conversion? What's my VA sub n going to equal? What's that? I can't hear you. Not 120. Think about this. Is this the line or the phase voltage? That's the line voltage, right? It was given as the voltage between the A line and the B line. So this is the line voltage. And essentially what I'm asking you for is a phase voltage, right? The voltage between the A phase and ground. And there was a conversion for that, was there not? Right? We said that the line voltage always equaled the phase voltage √3 with an extra 30 degrees of phase. So essentially now I want to work this backwards. Instead of being given the phase and getting the phase voltage and getting the line voltage, the problem is essentially by using a delta configuration, they're giving you the line voltage, and in order to do the easy solution, you need to get the phase voltage back. So you say phase voltage is VL over √3. And what do I do with that phase angle? I subtract 30 degrees. Right, it's just the backwards. Right, it's the reverse operation. So what's my source going to be? It's going to be 208 over root 3 angle minus 30 degrees. All right, is that how I did it in my paper? It totally is. So you get 120 volts RMS. It basically turns into the exact previous problem, except they use different impedances. All right. So let me do this. I think I'm out of time for today. What I'd like you to do for Monday, I'm going to give you a little homework over the weekend. Don't hand this in. I know you've got other stuff to do. But please try to work example E11.8. It's a good example. In E11.8, both the source and the load are delta configured. All right, and they ask you to get the line voltages. So I think what I'd like you to do is to try it at home, because it's one of these. They don't actually work the problem in the book; they just give you the final answer. So I was actually able to get the same answer as them, but I'd like to see if you could get the same answer as them. So try it, and then probably what I'll do is just post a solution for that, after Monday. But I would like you to try it over the weekend. I think this is a good chance to see if you're actually making sense of this stuff. All right? Okay, I won't be here on Monday, but Dr. Piccone will. So feel free to ask him what Circuits 2 is going to look like in the spring, and let me know, because I don't know.